Today we are going to install a highly available K3S Kubernetes cluster on 3 AlmaLinux servers. K3S is a lightweight Kubernetes distribution developed by the SUSE and Rancher team and is geared towards edge, IoT and ARM deployments. That makes it perfect for smaller clusters on not so beefy hardware. We will use it to deploy a new cluster with an embedded etcd database for high availability. That way, if one of the servers should fail, the cluster will resume operations, since all the data in the etcd database is replicated between the nodes. All my nodes will work as a control plane and agent at the same time. That is fine for smaller clusters and development environments, but if you want to deploy bigger, production-grade clusters, you should have dedicated nodes for the control planes. I started by installing 3 AlmaLinux 9.2 servers without any special configuration. After that I installed the latest updates, some basic tools like Vim, and gave my user tux sudo privileges. At last I opened the necessary ports in the firewall to enable communication between the nodes. K3S provides a handy bash script to streamline the installation process. You can fetch the script with curl and execute it with the necessary parameters. The script will then download the needed packages and configure the systemd service for you. Since we are starting from scratch, we need to initialize a new cluster. Therefore, I am connected to the first server and will give the following parameters to the script. The K3S token is a shared secret and will be needed to join other nodes to the cluster. You can set it to whatever string you like, but you should save it somewhere if you would like to add additional nodes later down the line. The server flag tells the script that this node will be a control plane. If you would like to add a worker instead, you can replace server with agent. The flag --init cluster will initialize a new cluster. This should only be done on the first node. If you will pass it on the other nodes too, you will get 3 separate clusters, and that is not what we want. Now you can see how the script is downloading packages and setting up the services. After a few seconds, the cluster will be up and running. Now our cluster is set up, but we cannot interact with it yet. Reason being that the configuration file for the cluster is owned by root and our user tux may not read it. So we have to change the owner of the configuration file. Now we can join the other nodes to the cluster. Therefore we will connect to the second and third server and will run the same script again, but this time with different parameters. We have to set the K3S token again to prove that we have permissions to join the new servers. The server flag is set again, since the other 2 servers are control planes as well. The first difference is the --server flag. It replaces the cluster init flag and tells the script to join to an existing cluster instead of creating a new one. Furthermore, we need to provide the URL of the first server. You can use DNS names if you want, but I will stick to the IP address to save the time needed for the DNS lookup and make the cluster independent from a working DNS server. This is generally a good idea when working with clusters. Let's create a simple Nginx deployment to give our cluster some work. First, define a namespace for the deployment. It's recommended to create a namespace for every application in the cluster. To create the namespace, we need to apply this configuration to our cluster. You can see the new namespace in our cluster. Now open the YAML file again. We will add the deployment next. A deployment describes which containers will be created. Again, apply the configuration. Now we can see an Nginx container being created. This is all good, but our web server lacks scalability. To achieve this, we need a horizontal pod autoscaler. The autoscaler will monitor the CPU usage of each container and will create more containers if one of them has an average utilization that passes our threshold. We can also specify the minimum and maximum amount of containers. If we increase the minimum, we can see how our cluster creates a lot of new containers. We can see that all the containers are distributed over all 3 nodes of our cluster. With the top command we can monitor the CPU and memory usage of all our nodes. Now, if we lower our maximum number of containers, the autoscaler will delete the excess containers immediately. If the number of containers is between the minimum and maximum amount, the autoscaler will wait and only destroy containers if they are not needed for about 5 minutes. If we want to reboot one of our nodes, we have to cordon and drain it. Cordon means no new containers will be created on this node. Drain means the existing containers get destroyed and rebuilt on other nodes. To re-enable the node, you need to uncordon it. Now a new container may be created on this node again, but no container will be moved immediately. At last we can watch how the autoscaler destroys the additional Nginx containers.